All right, in 11.3, we are looking at gas stoichiometry. We've already actually done a little bit of gas stoichiometry. We have related compounds through a balanced equation in relation to the volume of space that they occupy. But I guess we'll do it in this section with a little bit more focus here. So 11.3 is gas stoichiometry. I'm going to move that out of the way, bring in this, and let's just start looking at problems because there's really no theory we need to talk about anymore. We've covered all the theory. It's really just a matter of being able to do some gas stoichiometry problems. So it says here that propane is a gas that's sometimes used as a fuel for cooking and heating. The complete combustion of propane occurs to the following equation. And now this is part of another question in your book on, if you look in your book, they ask you what will be the volume of oxygen required to complete the combustion of this gas. So, but I'm going to pick some different numbers here than they have in your book. So let's say we have half a liter, 0.5 liters of propane. What I want to know is how much oxygen do we need to react with it? Because, like we've spoken of before, if we don't have enough oxygen, then we don't have what's called complete combustion. We have incomplete combustion. And remember, incomplete combustion makes carbon monoxide. So it actually is incredibly important that we have enough oxygen to fully react with our 0.5 liters of propane that we have. Okay, so I have 0.5 liters of C3H8. And what I want to do is, again, convert it to oxygen. Well, again, if we're talking about two gases, this is a gas, this is a gas, and we assume that we are at the same conditions, and in this problem, we don't have any reason to assume our conditions change. And if they're reacting, if they're touching each other and reacting, well, then those gases have to be at the same conditions. Well, then we can use that molar ratio in the balanced equation, again, as a gaseous ratio. So 1 liter of C3H8 will react to produce react with 5 liters of oxygen, not produce. Oxygen is a reactant. So we need 2.5 liters of oxygen. So it can be that easy with gas stoichiometry. Now, it is not always that easy because we're not always dealing with one gas and going to another gas at the same temperatures and pressures. Notice here's a sample flow chart of what we might have to do at some point. So if we have the volume of gas A, so if we have the volume of that gas, we may often have to convert it into moles. And notice right here they have standard molar volume. Well, that's going to be great. That's our standard molar volume. That is that 22.4. That's the molar volume of gas at 1 mole. Notice, though, it only works at STP. So we can't always use the standard molar volume of a gas, only if we're at STP. Now, a lot of our problems are going to be at STP. And so we can use that relation to change things into moles. Once we do that, well, we can go from moles of one thing, again, to moles of another using the mole ratio. We've done that numerous times, and then out to maybe a mass of a reactant or a mass of another reactant. So let's look at the problem that they have. The problem that they have listed with this says that we have 10 liters of ammonia. They're being produced in this equation. How many grams of ammonia were produced? Now notice this one is actually a little bit silly. It doesn't say that it's at STP. I guess we have to assume that it is. So notice what they do is they change that into moles, and then they're changing it into mass. So they're actually not using the balanced equation for this, and we don't really need a balanced equation because it's asking about a single gas. In this case, the only thing that's missing is we'd have to put those 17.03 grams on top to solve this problem. Now, I kind of like this flowchart a little bit better because it's a little bit more accurate. Because remember, what we can do is we can relate, as in that first problem, the volume of one gas to the volume of another, again, if they're at the same conditions. So notice F, we can apply the volume ratio just like we would a mole ratio through the balanced equation, again, if it's at the same conditions. Otherwise, what we may have to do, again, is convert that volume into moles to moles of whatever else we're doing, and then out to a mass, or perhaps out to another volume. Now, one thing we can do is, these all say apply the molar volume of 1 mole equals 22.4 at STP. If we're not at STP, I'll just warn you that then we might have to convert between volume and moles, and the way we would end up doing that often is using PV equals nRT. So we might have to substitute in our ideal gas law, again, if our conditions are not as standard, or if our conditions are changing during the experiment. Okay, what I'd like to do is some of your section review problems, if you don't mind me doing them. And again, this is a great time to pause it, see if you can figure them out, and then turn the podcast back on and see if you set them up the same way, or see if I made any errors as well. I've been waiting for somebody to tell me I got something wrong. I haven't heard anything yet. Maybe I'm perfect. I kind of doubt that, though. So it says, how many liters of ammonia gas? Ammonia gas is NH3 is ammonia. It's a gas. Can be formed, so that is our product that we're forming, from the reaction of 150 liters of hydrogen. So we have hydrogen gas, 150 liters. Notice there's a decimal at the end, meaning we have exactly 150 liters, so there's 3 significant figures in that value. Assume that there's a complete reaction of hydrogen with excess nitrogen. So we have nitrogen gas in excess. Again, if it's in excess, we don't have to worry about calculating it. Now we could have a limiting reactant problem with gases. That happens occasionally. And that's just fine. We would solve it like we would any other limiting reactant. Anyway, this one's not. All measurements are made at the same temperature and pressure. So that's important, because if they're all made at the same temperature and pressure, remember, then what we can do is we can go back and we can use this relation. We can do exactly like we did in this first problem, where we just treat that molar ratio as a gas ratio. So this problem is really, really easy, right? So if we have 150 milliliters of hydrogen, and we want to know how much ammonia we make, well, again, the molar ratio will work as the volume ratio, because our gases are all at the same conditions. 3 liters of hydrogen will produce 2 liters of ammonia. And that is simple gas stoichiometry. So 2 times 150 is 300. 300 divided by 3 is, thank you, Mr. Johnson, 100 liters of ammonia. There we go. Let's scroll down now and do number 2. How many liters of hydrogen gas at STP can be produced? So notice we're at STP. So that's 1 atmosphere of pressure, and 0 degrees Celsius can be produced by the reaction of 450 grams of sodium and excess water, according to it. Now we're getting kind of interesting. So now we have a mass, and we want to solve for how much gas it's going to produce. So we have a stoichiometric problem. So that's great, because I wanted some actual stoichiometry here. So we have 4.06 grams of sodium. Now, first steps that we did with these, and we can go and we can look at one of these flow charts and follow it if you need to. I mean, that is definitely something to have handy if it's something that helps us solve these. So I have a massive amount of reactant, and that reactant is sodium. First thing I need to do is change it to moles. How do we do that? If we look down here, it gives us our hint, our molar mass. So the molar mass of sodium is 22.9. I'll use 23 grams. I'm going to round off here. I hope you aren't offended by my severe rounding. I'm changing into moles. Now what do we do? Well, just like any other stoichiometric ratio, we have to look at the mole ratio. 2 of these produce 1 hydrogen. So 2 moles sodium produce 1 mole of hydrogen. I wonder if you thought you were going to be done with stoichiometry after the last chapter. Luckily, we're not. We still get to do some more. Okay, so now what do? Now notice hydrogen is a gas. We want liters of gas. Luckily, we're at STP, and we know the relation at STP, 1 mole equals 22.4 liters. So I can plug that in on the end. 1 mole of hydrogen is going to produce 22.4 liters of hydrogen. Now, if I go through this problem, notice not too terribly bad. 4.6 divided by 2 is 2.3. 2.3 divided by 23 is about 0.1. 0.1 times 22.4. We should get about 2.24 liters of hydrogen, I believe. So that was kind of fun. Gas stoichiometry, it's a good time. Number 3, how many grams of sodium are needed to react with water to liberate 4.00 times 10 to the second milliliters of hydrogen gas at STP. Okay, so now we're starting with the gas, and we want to solve for the mass. So basically we're going to run the same problem backwards. So now we have 4 times 10. So we have 4 times 10 to the second milliliters of hydrogen. Well, the first thing is, again, our molar volume that we have is in liters. So we have to change this into liters. So the first thing I will say is 1,000 milliliters is 1 liter. So I've changed it into liters, so I have to divide that by 1,000. Not a big deal, hopefully. Now, again, we want our answer in moles. We are starting with a gas. It does say it's at STP. So we're going to use this molar ratio that we used in the previous problem. But now we want to get rid of these liter units. So the 22.4 will go on the bottom. 22.4 liters of hydrogen gas is 1 mole of hydrogen gas. And now I'm into the middle of my stoichiometry. I'm into moles of hydrogen. So now I need the ratio with sodium. while the ratio with sodium hasn't changed from the previous problem, the only thing that's changed is how we represent it. This time 1 mole of hydrogen is on the bottom, and 2 moles of sodium is on the top, because that is what I'm solving for. Last bit, I'm going to change my moles of sodium into a mass, 23 grams of sodium. So notice it is actually all the same values, because I'm going now from hydrogen to sodium. The previous problem I was going from sodium to hydrogen. This one I should be ending in a mass of sodium that is needed to produce that hydrogen gas. Again, important, it is at STP. So let's take a look at it. When I run the numbers through, I believe this is right. I have 0.4, so 400 divided by 1,000 is 0.4. 0.4 times 2 is 0.8. 0.8 times 23 divided by 22.4 is going to be about 0.82 grams of sodium is what I get. Or actually 0.821 I should report it as, because notice this does have 3 significant figures, so I should be a little bit careful with my significant figures. 0.82 isn't really correct. I should have 0.821 grams of sodium. Okay, now one more problem here, and I'll scroll back up to see what it is. What volume of oxygen gas? Actually, maybe I can erase this so it doesn't get too far down the page. All right, so what volume of oxygen gas in liters? So my oxygen gas is here. I want in liters. That's where I put my question mark. Can be collected. Oh, look at this. This is nice. Now we have something that does not have STPs. We are not a standard condition, so we're going to have to use our PV and our T. How much oxygen can be collected when 30.6 grams of potassium perchlorate decomposed by heating according to the equation? Okay, I'm still going to start this as stoichiometry, right? Because I have my potassium perchlorate, I still need to know how many moles of oxygen. So first thing, I'm going to divide this by the molar mass to get moles. I want 1 mole of potassium chlorate, and that is 122.5 grams of potassium chlorate. Once I divide by the molar mass, I'll have moles. Now I look at the ratio, it is 2 to 3. So 2 moles of KClO3 gives me 3 moles of oxygen. And now here is normally, again, if it was at STP, we could throw in that molar volume of gas. We could put in 22.4. But notice we are not quite at our STP. We're pretty close, actually, to what's called SRP, our standard room pressure and temperature. But what we're going to have to do is we don't have a good constant that we can throw in there that we know. So we're just going to have to solve for moles right now. So we have 0.37 moles of oxygen. 0.37 moles of oxygen. Now, that's not the volume. Okay, what happens is if we're not at STP, we're going to have to refer to our ideal gas law to solve for it. So we have to use PV equals nRT. This we solve for. Now we know the moles. The equation gave us the temperature, 25. So our temperature is 25 degrees C, and our pressure is 0.98. So we have a pressure of 0.98 atmospheres. So notice we can solve this. We have all the values we need to solve it. We have a pressure, we have moles, we have temperature, and R is our gas law constant, 0.0821 is what we're going to use. So we can rearrange this equation for V. I'm going to divide both sides by P, and I'll get V equals nRT over P. Now I'm going to put in all my numbers in the right values. I have 0.37 moles of O2, right, times R, 0.821. And I'm leaving off the units on R, which I probably should not. It's just hard to squeeze them in. Now my temperature, remember, temperature always has to be in Kelvin. So it's 273 plus the 25, so we're at 298 Kelvin. 298.15 if we want to be very particular. And pressure, notice it is already in atmospheres, which works with the R that we're using, so we don't have to convert it. So my volume now, after I solve this equation, is 9.29 liters of oxygen, right? So we also want to completely label what we have, the units, and what species we're talking about. So